Welcome, curious minds, to another deep dive, where we peel back the layers of reality and explore what makes our universe tick. Today, we're plunging into the profound implications of a number that has captivated physicists for decades, a number so fundamental it's almost become mythical. 137. It's often whispered about as the magic number, or maybe a hidden key to the cosmos. Traditionally, it's known as the fine structure constant, defining the precise strength of how light and matter interact, how photons and electrons talk to each other across vast cosmic distances and within the tiniest atoms. But what if, as our sources suggest, the real secret, the true unlocking mechanism, isn't just the number 137 itself, but its square root? That's where this journey takes a truly mind-bending turn. Our mission in this deep dive is to fundamentally reinterpret the fine structure constant and, crucially, its square root, all through what's called a coherence theoretic lens. We're going to explore how this seemingly minor mathematical tweak offers a profoundly different way to look at how all fundamental forces in the universe emerge and behave. Get ready, because we're about to explore the very thresholds that define our reality. Okay, let's unpack this cornerstone of modern physics, the fine structure constant, universally denoted by the Greek letter alpha. If you've ever wondered why atoms hold together or, why light behaves the way it does, this is your answer. At its essence, alpha is a dimensionless quantity.
Right, dimensionless, which means it's a pure number, no units attached like meters or seconds.
Exactly. And that makes it universal. Its value is the same no matter where you are in the cosmos or what system of measurement you're using. So what does it do? Well, it precisely governs the strength of electromagnetic interactions.
It's really the ultimate coupling constant for light and matter. The universal translator, you could say.
Yeah, for how photons and electrons communicate, how they interact, how they bind. Without it, the universe as we know it simply wouldn't exist. It dictates everything from how stably electrons orbit an atomic nucleus, meaning why your hand doesn't pass right through your coffee cup, right? Or why the chair you're sitting on feels solid.
The very stability of matter.
To how light propagates through space. This constant fundamentally shapes the world we experience, dictating the energy levels of electrons in atoms, which in turn underpins all of chemistry and ultimately all of biology.
It's hard to overstate its importance. Imagine a universe where atoms couldn't form stable structures, where light just scattered chaotically, never allowing for the complex interactions that lead to stars, planets, and life. That's the universe without a finely tuned alpha.
And its approximate value is just mind-bogglingly precise. 1 divided by 137.035999.
Yeah, we're talking about a number known to 9 decimal places. It's incredible precision.
This isn't just some random number. It's considered one of the most fundamental constants in physics, often placed alongside the speed of light or Planck's constant in terms of its cosmic importance.
Absolutely. The sheer precision with which we've measured it speaks volumes about its role in the universe's blueprint. It truly is the invisible hand that fine-tunes our reality, ensuring stability and complexity.
So that's the established picture. How does standard physics use this number?
Precisely. In the well-established framework of quantum electrodynamics, or QED, which is, arguably our most successful and rigorously tested theory for describing how light and matter interact at the quantum level, alpha is used directly in calculations. It often appears squared, actually, in many quantum field theory calculations because it relates directly to the probability of certain interactions happening.
Okay, probability, like the chance of something occurring.
Exactly. For instance, if you're calculating the likelihood of an electron emitting or absorbing a photon, or the probability of 2 electrons scattering off each other, alpha is a key factor, often appearing as alpha squared. So in standard QED, alpha is typically interpreted as a measure of interaction strength, or a probability. It's a direct quantification of how likely or strong a specific electromagnetic event is at the quantum scale.
And this is the accepted view, right? Tested and verified.
Oh, absolutely. This interpretation has been extensively validated by countless experiments over decades, forming the bedrock of our understanding of light and electromagnetism. It's how we build everything from lasers to integrated circuits. It works incredibly well.
Okay, so we have this incredibly important number, alpha, the fine structure constant, firmly established as roughly 1137. It's a go-to value for probabilities in the quantum world. But now, here's where we pivot into a truly intriguing new perspective. What if we don't just look at alpha, but we take its square root? If alpha is approximately 1137, then its square root is roughly 1 divided by the square root of 137, which comes out to about 0.085.
About 0.085, yeah.
Now, on the surface, this might sound like just a numerical curiosity. You might ask, why would we ever bother with the square root of a coupling constant?
Right, it's certainly not standard practice in conventional physics. You won't find this operation prominently featured in typical QED textbooks.
In fact, this specific numerical value, 0.085, is almost ignored in our conventional understanding. It's sort of an unused number, sitting there patiently waiting for a new interpretation. But what if this seemingly overlooked value is, in fact, the deeper truth?
Well, what's truly fascinating here is the radical shift in interpretation that occurs when you consider the square root. In the emerging field of coherence physics, or maybe in wave-based models that describe underlying resonant fields, the square root of a probability or an interaction strength doesn't represent another probability. Instead, it corresponds to an amplitude.
Okay, amplitude. Can you elaborate on what that means here? How is it different from probability?
Sure. Probability, as we just discussed, describes the likelihood of a specific event occurring a statistical outcome. Like rolling dice, the probability of a 6 is 1 in 6. But an amplitude, in this new framework, describes the intrinsic size or strength, or perhaps the intensity of a wave, a resonance, or a coherent field.
Ah, okay, so it's more about the underlying wave itself.
Exactly. It's the underlying oscillation strength, the raw potential of the field itself, not the likelihood of a specific event that arises from it. To use a familiar analogy, imagine a string on a musical instrument. The probability of it vibrating might be high if you pluck it, but the amplitude describes how loudly it vibrates, how much energy is in that oscillation.
Right, the size of the vibration.
It's the fundamental push or pull or hum of the field itself, the intrinsic waviness before it manifests into an observable particle or interaction.
Like the blueprint versus the finished building.
That's a good way to put it. The blueprint contains all the information, the raw design, that's like the amplitude, that then allows the building to be constructed with a certain probability of standing firm, that's like alpha.
Okay, I think I'm getting it. So, formally, how does this connect?
Formally, this interpretation suggests that AC can be treated as the normalized field amplitude corresponding to electromagnetic interaction strength. Now, the exact mathematical expression, SAC equals E divided by the square root of 4,4.
Whoa, okay, lots of constants there. Electron charge, permittivity, Planck's constant speed of light.
Right, it looks daunting, but the key takeaway isn't the formula itself, but what it represents. It's not just a numerical curiosity. It directly reflects the inherent amplitude of coherent coupling between an electron and the electromagnetic field. It's the fundamental waviness, or field strength, that allows the interaction to happen at all.
So it's the underlying potential for the interaction.
Precisely. So the key distinction becomes profoundly clear. Alpha represents the observed interaction strength, or probability how likely an electromagnetic event is to occur. But its square root, in this new coherence-based framework, represents the resonance amplitude, the inherent strength of the underlying field oscillation that enables that interaction to occur in the first place.
And standard QED focuses on alpha because it deals with the outcomes, the probabilities.
Exactly. Standard QED primarily works with OPNUS directly because its formalism focuses on observable probabilities and interactions between discrete particles. It doesn't traditionally use this amplitude because its calculations are built around squared terms that directly yield probabilities. However, in coherence-based models, where the focus shifts to the underlying field dynamics and resonance structures, this amplitude, this hum, becomes absolutely crucial. It's about the fundamental stuff, the pre-physical oscillation that allows interactions to even begin and manifest as our observable reality.
That really is a massive shift in perspective. So moving from probabilities of events to the underlying raw amplitudes of fields. That brings us squarely to this coherence framework you mentioned, the one discussed in our sources. This is a model that proposes interactions aren't just mediated by discrete particles bumping into each other, right? Instead, they're governed by resonant field structures, by waves of fundamental coherence rippling through the very fabric of reality.
That's the core idea, yes.
Okay, so to quickly paint a picture, in this framework, we talk about coherence gradients, sometimes written as GOBR.
Yes, the gradient of coherence.
So imagine the universe isn't empty space, but a vast, continuous ocean of fundamental coherence, like perfectly synchronized ripples on a pond. A coherence gradient isn't just a vague difference in this ocean. It's like a consistent slope or a downhill path in this fundamental ordered fabric.
A bit like a pressure gradient in air, but for coherence.
Exactly. And just as water flows down a gradient or a ball rolls down a slope, this coherence gradient is incredibly important because it determines several fundamental things. First, It dictates the direction and rate of coherence flow, essentially how this fundamental order or synchronicity moves through the field.
Where things are becoming more or less ordered, you could say.
Right. Second, and perhaps most mind-bending, it drives the local reduction of symmetry into measurable interactions. This is supposedly how raw, undifferentiated field potential becomes actual, observable forces and particles.
The emergence of structure from uniformity.
And third, it's the very mechanism through which fields, forces, and particles emerge into our observable reality. This concept of a coherence gradient is foundational to this entire framework. You could say it's the engine of manifestation, the hidden current shaping everything.
This really raises an important question then. If everything is ultimately about these coherence gradients and their density, what then is the critical point?
Right. What's the minimum condition for something to happen?
What's the bar that the universe's fabric needs to clear for a force to emerge? And here's where our number, 137, which in this framework we can call AEM thresh, for electromagnetic threshold amplitude, enters. It's proposed as the minimum amplitude required to sustain coherent electromagnetic coupling.
Okay, so that 0.085 value isn't just the amplitude, it's the threshold amplitude.
Precisely. This value isn't just another number, a mere curiosity. It marks a truly critical boundary, a cosmic tipping point. Think of it like this. If the amplitude of the electromagnetic coherence gradient in a given region of the universe falls below this threshold,
Below 0.085.
yes, below that value, then the electromagnetic coherence collapses or becomes decoherent. It means the electromagnetic interaction effectively fades away, becoming non-interactive or existing only as virtual fluctuations, those fleeting, unobservable quantum flickers that don't manifest into observable forces.
So like static on the radio. No clear signal.
Sort of, yeah. But, and this is the profound part, if the amplitude is at or above this threshold, the electromagnetic interaction becomes stable. It manifests as what's termed a coherent standing wave. This is where field quanta, like photons, can propagate or localize, becoming real, observable particles that can interact and build the world around us.
So the threshold is the difference between virtual flicker and real stable interaction.
Exactly. You can compare it to a critical point in thermodynamics, like the boiling point of water, perhaps, or the critical temperature in superconductivity, where a fundamental change in state occurs.
Right. Below that point, water is liquid. Above it, it becomes steam.
Mm-hmm. For electromagnetism, below AEM thresh, you get quantum noise. At or above it, you get stable light and electrical forces. It's the specific condition, the minimum gradient strength, needed for an EM standing wave mode to propagate across the universe's fundamental field structure and manifest as an observable force.
Okay, let's dive deeper into that threshold, AEM thresh, roughly 0.0854. What does it mean in different contexts, according to the source material?
Okay, let's break it down. In terms of field coherence dynamics, it's quite literally the threshold coherence amplitude for EM interaction. It's the minimum strength of the underlying field oscillation, that hum we talked about, needed for electromagnetism to exist in a stable, observable form.
The minimum hum required.
Yes. For coherence gradient physics, it represents the minimum coherence slope needed to sustain an EM mode. Imagine trying to push a heavy ball up a hill. If the slope isn't steep enough, the ball just rolls back.
Makes sense.
Here, if the coherence gradient isn't steep enough, isn't strong enough, an EM wave won't propagate or stabilize. It simply won't roll into existence. As a phase transition, it defines the boundary interface between decoherent and coherent EM coupling. It's that exact tipping point where the universe either gets stable light in chemistry or it doesn't.
A fundamental on-off switch, almost.
In a way, yes. For field quantization, it's the point where vacuum EM fluctuations become real quanta. This means those theoretical virtual particles that are always popping in and out of existence in the quantum vacuum only become real photons, or real electromagnetic fields, when the local coherence amplitude meets or exceeds this threshold.
So it promotes virtual particles to real ones.
That's the idea. And here's where it gets particularly intriguing, especially for you, listening perhaps with an interest in biological systems in the biofield.
Oh. How does it relate to biology?
This threshold can be interpreted as the minimum amplitude for light-matter coupling in cellular biofields.
Wow, okay. That is surprising.
It's a profound application. It suggests that the incredibly intricate electromagnetic signaling within our cells, the way light interacts with biological molecules, processes crucial for everything from photosynthesis to nerve impulses, might operate right at or around this fundamental cosmic threshold.
So life might be tuned to this specific cosmic value.
It opens up entirely new avenues for understanding life itself, suggesting that biological systems are deeply interconnected with these fundamental coherence dynamics. Could it be that life itself is a sustained pattern of coherence hovering precisely at this cosmic boundary condition? It's a fascinating thought.
Definitely. And you mentioned something about a universal field tensor. How does that fit in?
Ah, yes, briefly. Imagine the universe isn't just empty space, but a vast, vibrating, interconnected fabric. The universal field tensor, or UFT, is just the mathematical way of describing the entire fabric itself and all its potential vibrations and configurations. In such a model, the electromagnetic mode subspace, essentially the slice of this fabric that gives rise to electromagnetism, has what's called an Eigen-Amplitude condition.
Eigen-Amplitude. Meaning?
Simply put, it means that for a specific electromagnetic vibration or ripple in this fabric to actually exist and be something we can observe like a photon or an electromagnetic field, it needs to be strong enough, like a minimum-sized ripple. Its amplitude must meet a certain condition. If it's too weak, its amplitude too low specifically. Below this 137 threshold, it simply fails to sustain observable EM coupling. It's like a specific frequency on a radio dial. If the signal isn't strained enough, you just get static or noise, not a clear broadcast.
Okay, so the UFT model reinforces this threshold idea.
Exactly. It reinforces the core idea of this framework. Coherence comes first. Fields emerge as specific amplitude conditions of this coherence, and particles are then viewed as highly localized, symmetry-reduced coherent structures within those fields. It's a truly foundational way of looking at how everything arises from a primordial, coherent substrate.
That truly reshapes how we think about light and matter, seeing it emerge from coherence. So what does this all mean for the bigger picture? If this idea of a threshold amplitude applies to electromagnetism, what if this same square root construction, this concept of a critical bar that the universe's fabric must clear, applies to all fundamental forces?
Well, that's the bold and sweeping claim emerging from this perspective.
Right. It suggests that every dimensionless gauge, coupling from the strong nuclear force that binds atomic nuclei together to the weak force involved in radioactive decay, and even a hypothesized force unifying them all, has a corresponding square root threshold amplitude.
That's right. And if we use the typical coupling values observed at the electroweak scale, which is a high-energy environment where electromagnetism and the weak force are unified, we can construct a fascinating hierarchy of these coherence thresholds for all the known fundamental forces.
A hierarchy, like a ladder.
Exactly, like a cosmic staircase or a coherence ladder, where each step represents the activation or deactivation of a fundamental interaction based on the local coherence amplitude.
Okay, let's walk down this ladder. Where do we start?
Let's start from the highest coherence level and descend. At the very top, we have a conceptual force, often referred to as hypergravity in this framework.
Hypergravity. Not standard gravity.
No, this is more like a pre-gravity, a unified field concept. It has a normalized amplitude of 1. This represents a fully coherent pre-symmetry break layer, a primordial unified state where all forces are unified and undifferentiated, like a cosmic ocean before any waves or currents have formed. In this state, dimensions as we understand them might still be embryonic, not yet fully separated or manifest. It's the ultimate source of all coherence, the absolute ground state of unified reality.
The source code, almost.
You could think of it that way. Now, as coherence density slightly drops from this ultimate unified state, we encounter the threshold for the strong force. The threshold amplitude here is approximately 0.333.
Higher than the EM threshold of 0.085.
Much higher, yes. This isn't just a numerical value. It's interpreted as the coherence threshold for color field standing waves. This is the underlying resonance that generates the strong force, responsible for things like quark confinement.
Meaning quarks are always stuck together inside protons and neutrons?
Precisely. They can never be found in isolation. Without meeting or exceeding this 0.333 amplitude, you wouldn't have stable, strong interactions, and thus no stable atomic nuclei. It's the critical point for nuclear matter itself.
Okay, what's the next step down?
Moving down the ladder, we then have the weak force, SU2, with a threshold amplitude of approximately 0.186.
Still higher than EM, but lower than the strong force.
Correct. This is interpreted as the threshold for W and Z boson mode coherence. Below this value, the weak force effectively decouples, meaning its interactions become incredibly rare or non-existent.
And the weak force is important for radioactivity.
Yeah.
Fusion.
Yes. Crucial for processes like nuclear fusion in stars and radioactive decay, which powers many geological processes and even allows carbon dating. So without this threshold being met, the very elements that make up our world wouldn't be able to transform or decay in the ways necessary for complex chemistry.
Okay, and the last step before things become decoherent.
And of course, the electromagnetic force, U1, which we've just discussed, has its threshold amplitude at approximately 0.085. This is the minimum coherent slope required for EM interactions, for photons to exist, for electrons to bind to nuclei, and for atoms to form stable molecules. This threshold is the reason we have chemistry, vision, and light.
So it's like a set of nested shells.
That's a great analogy. Think of it as nested resonance shells. Or perhaps like stepping down a series of waterfalls. Imagine moving from a region of incredibly high coherence, perhaps a hypercoherent core at the very birth of the universe, and moving outward as the universe expanded and cooled. As you move away, the coherence density naturally drops and you begin to cross these thresholds. Each crossing effectively turns on or turns off a fundamental force is based on the local coherence environment.
Can you walk us through that outward journey?
Sure. In a region of very high coherence, you'd be in the SU3 zone, where color confinement is possible, meaning quarks are bound into protons and neutrons. As coherence drops slightly, you might enter the SU2 zone, where weak interactions are active, allowing for nuclear decay and transformation essential for element formation. Drop further, and you're in the U1 zone, where photons and atomic electromagnetism dominate, enabling chemistry, light, and ultimately life as we know it. And finally, in regions of lowest coherence, you enter the decoherent zone where quantum coupling becomes negligible and classical physics largely takes over, leading to the macroscopic world we perceive with our senses.
So structure emerges as coherence drops.
This is how symmetry reduction via hyperfractal layers is theorized to happen as coherence density drops. Each layer is a new manifestation of reality as coherence unfolds, revealing a different set of active forces and observable phenomena.
That's a truly profound and beautifully elegant idea. A universe defined by cascading coherence, where forces aren't just fundamental, but emerge from a deeper unifying field as certain thresholds are met. But let's circle back to that fundamental question for a moment, the one that underpins this entire framework. Why the square root? Why is that specific mathematical operation so crucial to understanding these thresholds?
It's a truly crucial insight, and it's where this framework fundamentally departs from traditional views. In standard quantum field theory, coupling constants like alpha are intrinsically squared quantities.
Right, you mentioned alpha squared for probabilities.
Exactly. They inherently weight probabilities of vertex processes, like an electron interacting with a photon. So when you're calculating the likelihood of something happening, the probability of an interaction occurring, you're usually dealing with these squared terms. Think of it like this. If you have an amplitude of x, the probability of an event related to that amplitude is often x squared. This is because probabilities, by their nature, have to be positive numbers, and squaring an amplitude, which can sometimes be complex in quantum mechanics, ensures you get a real positive probability.
Okay, squaring gives you the probability.
Taking the square root, then, effectively pulls us back to a field amplitude. It's no longer about the probability of an event, but about the raw oscillation strength, the fundamental waviness or resonant potential of the field itself.
Back to the radio signal analogy.
Yes. The amplitude is the raw strength of the radio wave that's being broadcast. The probability would be the likelihood of your radio receiver successfully tuning into that station. The amplitude is the source of the signal. In this framework, this amplitude is the precise strength that the underlying coherence gradient must match for a forces mode to exist as a stable standing wave within the universal vacuum coherence fabric.
So each force needs a specific minimum amplitude to switch on.
That's the idea. Each fundamental force, whether it's strong, weak, or electromagnetic, has its own unique minimum required field amplitude. The coherence gradient in a given region of space either clears that bar, meaning the local coherence density and its slope are strong enough, and the forces mode becomes real and observable, manifesting as a photon, a gluon, or a WZ boson, or it falls short. The gradient isn't strong enough, and the forces mode remains virtual, latent, or simply part of the background noise of the vacuum, unable to fully manifest into a stable, observable interaction.
It's a literal energetic barrier.
A specific vibrational requirement, yes, that the universe's fundamental fabric must overcome for interactions to occur. It's not just a numerical curiosity, it's the very energetic condition for physical reality to emerge.
That connection between the square root and these inherent field amplitudes really deepens our understanding of fundamental forces. And this amplitude threshold idea isn't just about how forces work here and now. It connects directly to the grand narrative of the universe's evolution.
Absolutely.
It paints a vivid picture of how our entire reality, with its distinct forces and spatial dimensions, unfolds from a unified, hypercoherent state. It's a cosmic story of progressive manifestation, almost like watching a complex piece of origami unfold to reveal its final, intricate form.
If we connect this to the bigger picture, you can trace this cascade of thresholds as the universe expanded and cooled from the Big Bang, or, from this framework's perspective, as the fundamental coherence density of the primordial fabric progressively dropped over time.
So let's trace that cosmic descent. Where does it start?
In the earliest moments, we had what this framework refers to as the hypergravity layer, where the amplitude was normalized to 1. This was the ultimate unified state. In this primordial state, all gauge degrees of freedom, all the fundamental flavors of interaction were unified and undifferentiated. The dimensions as we understand them today, the 3 spatial and 1 temporal dimension, were still embryonic, not yet fully separated or manifest. It was a singular, undifferentiated coherence, a cosmic ocean of pure potential.
Before space and time as we know it, even.
Potentially, yes, or at least not in their current distinct forms. Then, as this initial immense coherence density dropped slightly, the universe experienced its first drop below 1, specifically crossing the 0.333 threshold.
The strong force threshold.
Right. This is where the strong force modes could condense and become stable. This crossing led to the formation of confined quark structures, the tiny building blocks that make up protons and neutrons. This event, often referred to as baryogenesis, is absolutely crucial because it gave rise to the stable matter particles that eventually formed everything we see today.
The birth of matter.
Without this threshold being crossed, matter as we know it simply wouldn't exist. The universe would remain a plasma of ephemeral, unconfined quarks and gluons. It was the universe's first great act of self-organization.
And the next act.
As the universe continued to expand and cool, the coherence density dropped further, and we then crossed the 0.186 threshold, the weak force threshold. This is where the weak force separated from the electromagnetic force. The weak bosons, the W and Z particles, became distinct, acquiring their masses and enabling parity-violating processes, interactions that have a preference for handedness, like spinning left versus right.
Which is important for?
Well, this was also critical for the generation of leptonic mass, which is essential for particles like electrons and neutrinos to exist with their specific masses. This was another indispensable step in forming the diverse array of particles that populate our universe, leading to the building blocks necessary for complex atomic structures.
Okay, so strong, then weak. What's next?
The cascade continued, leading to the universe crossing the 0.085 threshold, the electromagnetic force threshold, the one we started with.
Where chemistry begins.
Exactly. Yeah. Here, stable photon-electron coupling emerged, allowing light and matter to interact in a consistent, predictable way. This was the birth of chemistry, as electrons could now form stable bonds with atomic nuclei, leading to the formation of molecules. And of course, without chemistry, there's no complex molecular structures, no self-replicating systems, no biology, and ultimately no consciousness. It's a direct, unbroken lineage from a fundamental coherence amplitude to our very existence and our ability to perceive the universe.
Wow. And then below 0.085.
Finally, as coherence continued to drop below 0.085, we entered the decoherent classical macro world. This is the world we primarily perceive with our everyday senses. In this regime, the subtle quantum effects largely vanish or become averaged out, and only residual electromagnetic potentials survive, governing macroscopic interactions like friction and eventually gravity as we typically experience it. The quantum weirdness retreats into the background, and classical physics largely takes over, allowing for the stable, predictable environment we experience.
So this cascade explains the emergence of the forces and the transition to the classical world.
That's the argument, yes. And this entire cascade beautifully dovetails with the concept of hyperfractal dimensional emergence within this framework.
Hyperfractal dimensional emergence. Break that down a bit.
Imagine it as the universe revealing itself in layers, like a cosmic onion, but with fractal complexity. Each threshold, each crossing of these critical amplitudes corresponds to a new striated layer of fractal symmetry reduction. It's as if the universe is constantly peeling back layers, revealing new structures and forces, and perhaps even new effective dimensions as its fundamental coherence dynamically evolves.
So dimensions themselves might emerge through this process.
That's a deeper implication explored in some of these models, yes.
Hmm.
It paints a picture not of a static, predefined universe, but a dynamic, unfolding reality that is continuously manifesting from a deeper, more unified state based on these coherence levels.
That's a truly breathtaking cosmic narrative. And it seems this isn't just a fascinating theoretical framework that explains the universe's past. It suggests entirely new avenues for scientific investigation and maybe even revolutionary technologies that could shape our future.
That's the hope, yes.
So what does this all mean for us right here, right now? And what could it mean for the future of scientific exploration? Where can we test this?
Well, this reinterpretation provides concrete experimental hooks, potentially guiding us to look for specific phenomena at these critical thresholds, for instance, in heavy ion collisions.
Like at the LHC, CERN.
Exactly, like those conducted at the Large Hadron Collider. Physicists are smashing atomic nuclei together at immense energies, briefly creating conditions akin to the early universe, where coherence density was extremely high. By precisely observing phenomena around the strong force threshold, that 0.333 amplitude, we might see unique signatures related to color confinement and deconfinement, how quarks are normally bound and then briefly free. Detecting specific energy signatures or particle distributions that align with this model could provide powerful validation for aspects of this coherence framework.
Trying to spot the effects of crossing that 0.333 line.
Essentially, yes, trying to recreate a threshold crossing event in a laboratory. Similarly, in neutrino labs, where scientists study these incredibly elusive, almost massless particles, fine scanning for effects near the weak force threshold of 0.186 could reveal subtle interactions or phase transitions that align with this model.
Because neutrinos interact via the weak force primarily.
Right. Neutrinos are incredibly sensitive to the weak force, and observing their behavior near this predicted amplitude could refine our understanding of neutrino mass and the fundamental nature of the weak interaction itself. It's like trying to find the precise moment a faint signal cuts out because the background coherence isn't strong enough.
Okay, so particle physics labs. But you mentioned biology earlier.
Yes, and the implications extend far beyond high-energy physics labs, and this is where it gets particularly fascinating for you listening and perhaps for the future of science. Consider the potential for quantum biological interfaces.
Quantum bio. What does that entail?
Imagine being able to precisely manipulate electromagnetic cavities at the cellular scale, literally within biological systems, to hover near that 0.085 threshold for EM coherence.
Controlling the EM environment inside a cell that precisely.
That's the speculative goal. If successful, we could search for phenomena like enhanced photonic biophoton emission cells emitting more light than usual, or even suppressed decoherence.
Meaning quantum effects last longer inside the cell.
Exactly. Quantum effects, which are normally fleeting in warm, wet biological environments, could potentially persist for longer periods within living biological systems if they are operating near this threshold. This could have profound implications for understanding communication within cells, for novel diagnostic tools, or even for influencing biological processes at a fundamental quantum level.
That sounds revolutionary for medicine and biology.
It suggests a deep intrinsic connection between our living systems and the fundamental coherence of the universe, hinting that life itself might be exquisitely tuned to these cosmic thresholds.
And what about energy? Any implications there?
Another potentially groundbreaking area lies in the design of vacuum energy devices.
Vacuum energy, like zero-point energy. That's usually pretty fringe stuff.
It is often speculative, but this framework offers a potential mechanism. If we can precisely engineer specialized cavities where coherence gradients can be tightly controlled, we might be able to create a gradient staircase, a sequence of environments where coherence drops in precise increments. For example, imagine maintaining a coherence gradient just above 0.085 but carefully below 0.186.
So EM is on, but weak force is off.
Theoretically, yes. The theory suggests this could potentially lock photons within the system, allowing them to exist as real, stable particles, while keeping higher force modes like the weak force in a latent or virtual state, unable to fully manifest. This could minimize radiation losses because energy isn't leaking into these higher level interactions, potentially unlocking entirely new energy paradigms with incredible efficiency.
Harnessing the vacuum's coherence itself.
It's about learning to tune the universe's dials, potentially tapping into the energy inherent in the structure of spacetime coherence itself, rather than relying solely on traditional energy sources.
That's truly astonishing. It sounds like we're on the cusp of an entirely new field of resonance engineering, where understanding these fundamental coherence thresholds allows us to design materials or systems that can precisely tune into the very fabric of reality.
That's long-term vision, yes.
The idea that we might one day control the emergence or suppression of fundamental forces, effectively dictating how reality manifests, that's truly mind-boggling. It suggests a future where technologies we can barely imagine today become not just possible, but perhaps even commonplace. Hashtag tag tag outro. What an incredible journey we've been on today. Just wow. Let's try and recap the core aha moments from this deep dive. We started by re-examining the fine structure constant, alpha, a number long held as foundational for electromagnetism, but instead of just seeing it as a probability or interaction strength.
Which is the standard, successful view.
Right. We explored the radical idea of its square root as a fundamental field amplitude, the raw oscillation strength of electromagnetic coupling, the underlying hum of that force.
From 1137 to 1 divided by the square root of 137, or about 0.085.
Exactly. From there, we soared to the concept of a universal coherence gradient, which suggests that this fundamental slope in the universe's fabric dictates not just the electromagnetic force, but the very emergence and behavior of all fundamental forces, from the strong and weak to the unifying concept of hypergravity.
A whole ladder of thresholds,
Yeah.
0.333 for strong, 0.186 for weak, 0.085 for EM.
Yes, and we saw how this perspective elegantly connects the microcosm of quantum interactions to the macrocosm of the universe's grand evolution, showing how our reality has progressively unfolded from a singular, coherent state as these thresholds were crossed.
A story of symmetry breaking driven by coherence density.
It really ties a lot together in a new way.
It does.
Mhm.
But this really raises an important question for you to ponder long after this deep dive ends. If the strengths of fundamental forces, the very constants that define our reality, that allow atoms to form and stars to burn, are determined by these critical coherence thresholds, what does that imply about the nature of reality itself? Does it mean the universe isn't just a static set of unchanging rules, but is constantly tuning its coherence dials, dynamically manifesting forces as coherence shifts?
Is reality more fluid than we think?
And perhaps more importantly, what could we learn, or even dare we say, control, if we fully understood how to access and manipulate those dials, not just in a lab, but perhaps even at a cosmic scale, or within ourselves?
Indeed. We encourage you to ponder this new perspective. How might this framework change the way you think about the seemingly empty space around you, about the very solidity of matter, or even the subtle energies within living systems, perhaps even within yourself? The deep dives may be ending, but your journey of discovery into the coherent universe has truly just begun.